This week, we'll explain the steps in the process of hypothesis testing, selecting appropriate alpha levels and explaining the selection, describing and performing a student's t-test, interpreting significance and meaningfulness of an independent t-test, and compare and contrast different t-tests. We will also explain when to use a one-way, two-way, or repeated measures ANOVA, and lastly, discuss the purpose of post hoc testing and describe situations when to use ANCOVA. Hypothesis testing is a process by which researchers move from hypothesis to inference. Researchers who use inferential statistics will follow a specific procedure of hypothesis testing as an objective way to show differences between groups. This usually involves creating hypotheses, setting probability levels, calculating critical statistical levels, performing the statistical analysis, and making a decision about group differences. Inferential statistics makes inferences about populations from research on population sample. This is where you compare groups of individuals who differ based on the independent measure, where one group is the treatment group, which will receive an intervention, such as a drug, while the other group is the control group, which receives no drug at all or an older drug. Hypothesis testing provides an objective measure of statistical differences. An important part of any research study is developing an appropriate statistical hypothesis. Remember that a research hypothesis should contain a pair of hypotheses that are statistically testable and opposite of each other. With inferential statistics, these hypotheses are related to group differences. One of the hypotheses is the null hypothesis, which states that groups do not differ from each other. For example, the treatment and control group score the same on the balance test after 10 weeks of training. Another way is to say that there will be no differences from pre-test to post-test. The other hypothesis is the directional hypothesis, which indicates that one group differs from another as a function of the independent variable. So for the directional hypothesis, you would say the treatment group scores are significantly higher on the balance test than the control group after 10 weeks of training. So when researchers are unsure about the direction of change, they can use a bidirectional hypothesis and use a two-tailed test to evaluate. In this case, you would say test scores will be significantly different from pre-test to post-test. Once you create the null and directional hypotheses, researchers need to set an alpha level. Since researchers cannot test every person within the population, they will randomly sample from that population in order to get a group of participants who appropriately represent the population. The use of inferential statistics is to objectively indicate whether sampled groups differ from each other, which we can then infer the results to the population as a whole. By selecting an alpha level, researchers limit the chance that they will incorrectly reject the null hypothesis or have a type 1 error, when in fact the null hypothesis should not be rejected. So when selecting the alpha level, this should be done before any statistical analysis. The most commonly used alpha level in research with human participants is an alpha level of 0.05. Some other alpha levels that are utilized is 0.01 and 0.001. However, if a researcher is doing pilot work, exploratory work, or proof of concept studies, they may use an alpha level of 0.10 or 0.15. For any beginners in statistics, and as mentioned in the previous slide, you need to select your alpha level before you run the statistics rather than after, as this is good practice. Another thing with the alpha level is that you can assign the alpha value as either a one or two-tailed test. A two-tailed test means that you split your alpha in half and test for a statistical significance in both sides of the normal curve. Two-tailed tests are frequently used, particularly if the researcher does not specify a direction within the hypothesis. A one-tailed test tests for statistical significance on only one side of the normal curve. But when using a one-tailed test, this provides more statistical power to detect differences, but should only be used when the direction of the difference is known. Once you have analyzed the data, you will need to make the decision to either reject the null hypothesis or not. The statistical software such as SPSS will provide the results of the statistical tests in the form of a p-value. And with this, you will need to make a decision based on the alpha level. The p-value indicates the probability that random error caused the sample differences that are observed. If the p-value is equal to or less than the alpha level, you will reject the null hypothesis and conclude that there are significant differences between groups. If the p-value is greater than the alpha level, you will accept the null hypothesis and conclude that there are no group differences. You can see from the example, when we are utilizing the most common alpha level of 0.05, that a p-value of 0.049 is less than 0.05. So this means you will reject the null. The p-value of 0.52 is greater than 0.05, which then this means that you do not reject the null or you accept the null. Not only do you have to make a decision about significance, but you also need to determine the meaningfulness of the results. Statistical significance indicates that a real difference occurs between the groups, but meaningfulness indicates the strength of differences. We can determine the strength of meaningfulness by calculating the effect size, which we discussed previously. A t-test is a statistical test used when comparing two groups on one dependent measure. It is characterized as simple, easy, and it's a pretty quick test to administer. It is represented as a lowercase t when talking about statistics. A thing with t-tests is that the calculated t must exceed the critical t-value to be significant, and also the p-value must be less than the alpha level. Next test we'll talk about is the student's t-test, which is a one-sample t-test. For the student's t-test, the researchers determine if a sample mean differs from the larger population on the dependent measure. This test can be used only if prior population data, such as age or gender norms, exist. The statistical formula that is used is the population mean minus the sample mean divided by the standard deviation for the sample mean times the square root of the number of observations in the sample. Let's take a look at this example. Imagine a local senior director wants to determine if the older adults at his center who have started a walking group within the past 6 months differ from the general population of seniors in their walking ability. To test this, you decide to test 30 older males between the ages of 70 to 74 years on the 6-minute walk test. The population mean is 612 yards within 6 minutes. But first, you'll want to create a null and alternative hypothesis, where the null hypothesis states that the sample mean is not different from the population mean. The directional hypothesis or alternative hypothesis is that the sample mean exceeds the population mean. After this, you will then set the alpha level at a value of 0.05. You will then put the data that you collected from the 30 older males into the software program and perform a test. The software program will give you the t-value, which you personally don't have to hand calculate. However, in this example, you can see the hand calculation to find the t-value, where t equals 3.108. Since you don't know the actual direction, you will then use a two-tailed test for the alpha level. The t-critical for a two-tailed test is 2.048, which is smaller compared to the t-value of 3.108. Therefore, you are going to reject the null that the population and sample means are the same and conclude that the sample group of 30 older males from the local senior center walked farther than the population mean on the 6-minute walk test. More frequently, you will want to compare two groups of participants to each other rather than a population mean. So the student's t-test is not appropriate then. You will then have to use other types of t-tests. In this case, it is the independent t-test. An independent t-test is used to compare two independent groups from the same population, or a single sample from two different populations, such as older versus younger. Another example is having one group receiving a treatment and the other not receiving a treatment. You can see the equation for the independent t-test is similar to the student's t-test, but with the addition of another group. So let's look at an example of an independent t-test. In this example, we're looking at the 6-minute walk test from two different senior center groups. Again, you'll want to create a null and alternative hypothesis. The null hypothesis will state that walking group 1 will not be different from walking group 2. The directional hypothesis will state that the walking group 1 will travel farther than walking group 2 during the 6-minute walk test. The alpha level that you're going to set is going to be set at 0.05. You can see in group 1 that the mean is 507 minutes with a standard deviation of 77 minutes with 15 participants. Group 2, the mean is 351 minutes with a standard deviation of 73 minutes with the same number of participants. You use a one-tailed test because you are hypothesizing that one group will travel farther than the other. After calculating, you get a t-value of 5.68. The t-critical value for a one-tailed test is 1.701. So since the t-value is 5.68 and is greater than the t-critical value of 1.701, You will reject the null hypothesis and conclude that the walking group 1 walks significantly farther than walking group 2 on the 6-minute walk test. A dependent t-test is used to compare two related data sets, such as pre to post testing. A dependent t-test is also referred to as a matched pairs or paired samples t-test. There will be at times where you may want to examine two groups that are related to each other in some way. So if you want to investigate the effects of an intervention, you'll want to compare the outcome or post-test to how the group performed before the intervention or a pre-test. This type of experiment is called a repeated measures design because the same measure is taken repeatedly on the same group of participants. For example, you may test the maximal strength of the participants before an 8-week training program and then test after the 8-week training program. When using a dependent t-test, this has several advantages over the independent t-test. One is that the participants act as their own controls, and secondly, they all receive the treatment provided. If you have a significant t-value, the next step is to determine the strength of differences between groups. You will usually calculate the effect size to provide an estimate of the strength of the group differences. Significance tells us that the groups are different, but the effect size tells us how different they are. For t-tests, though, you will calculate Cohen's d for an estimate of effect size. The value of Cohen's d will range between the value of 0 and 2, where a value of 0.20 is small, a 0.50 is medium, and a 0.80 and above is going to be large. When you want to investigate differences among more than two groups or between two groups at multiple time points, you can perform a test called analysis of variance, or ANOVA in short, which allows for multiple comparisons. You may ask, why can't you just perform multiple t-tests? Well, it can get complicated with more than 3 comparisons, and it will also compound type 1 error. With ANOVA, this compares the variance between and within groups. Variance between groups represent how the groups differ from the population mean, and the variance within groups represents how individuals differ from the group means. If the variance between groups is similar to the variance within groups, then this suggests that the treatment does not have an effect. The symbol for the result of an ANOVA is F, also known as the F ratio. There are different types of ANOVAs, such as one-way ANOVA, repeated measures, and a two-way ANOVA. The one-way ANOVA is the most basic form of ANOVA, which is basically an extension of the t-test to include 3 or more groups. So let's say that you want to compare the effect at 0, 20, 40, and 60 minutes of training, and with this, each time value represents a distinct level of that factor. One thing to consider is that if you have 3 or more groups, you'll need to perform a post hoc test, which is necessary to determine which groups differ from each other. Here in the example, we want to compare the impact of walking for 45 minutes at a target heart rate zone for 2 versus 4 days a week, with 0 day a week being the control group over a 10-week period. In the table to the left, you'll see that each group contains 10 participants with their respective data. You'll still want to follow the same procedures as you did with the t-test, where the null hypothesis is that no differences exist among the groups in the 6-minute walk test, and the directional hypothesis is that the 2 and 4 times per week walking groups will travel farther on the 6-minute walk test compared to the control group. Again, we'll set the alpha level at 0.05, and then after that you'll run this data through SPSS. Significance is evaluated by comparing the F actual value, or the F value, to the F critical value, which the F value in this example is 7.833 and the F critical value is 3.354. You can also see that the p-value is 0.002, so since the F value is greater than the F critical value, the null hypothesis is rejected, indicating that there are differences among walking 0, 2, and 4 days per week. There'll be at times that you want to show that some sort of change over time occurs. To show that an intervention works, participants need to take a pretest and a post-test, or perform multiple testing points throughout the intervention. In theory, if the intervention worked as planned, the test results should be significantly different from each other, or each different time point should be significantly different from each other. A repeated measures ANOVA is used when a dependent variable is measured more than once within a group. So what you are doing is tracking changes over time in the dependent measure. When just using a single group of participants and performing a repeated measures ANOVA, the participants act as their own controls. This controls for individual differences in participants, which is a substantial source of variation or error within studies. You can also perform a repeated measures ANOVA that includes 2 or more groups. A two-way ANOVA is used with two or more independent variables, which are called factors. For example, we know that intensity of exercise is one independent variable that can impact VO2 max, but so can frequency of exercise. We can then manipulate both intensity and frequency and then compare their effects, both independently and together, in one test, which is a two-way ANOVA. Unlike a one-way ANOVA, a two-way ANOVA allows for the evaluation of interactions between the independent measures. An interaction is the effect of two independent measures acting together on a dependent measure. There could be an interaction between frequency and intensity. We can also look at the impact of just frequency alone and just intensity alone. So just looking at the sole independent measure, this is called the main effects. With the main effects, all data are compared on one independent variable and pooled on the other independent variable. Some characteristics of a two-way ANOVA is that each factor has at least two levels. The symbol for the result of a two-way ANOVA is the letter F. To determine if there is significance, we will look at the F value and the P value. We then can see if there is significance of the main effects or if an interaction occurs. So here we have an example of a two-way ANOVA. The research question is, what is the effect of frequency and intensity on maximal oxygen uptake? We can see that factor 1, or one of the independent variables, is frequency, with weekly training sessions of 3 or 5 days as the levels. Factor 2, or the second independent variable, is intensity, with percent of maximum heart rate of either 65% or 85% as the levels. So the total groups would be 4 for this study. Similar to all the other tests that we talked about, you want to develop a null and directional hypothesis. The null hypothesis states that no differences exist among any of the 4 groups in their VO2 max. The directional hypothesis states that the groups will differ in their VO2 max. So we set the alpha level at 0.05 and then collect the data. Once you collect the data, you input it into SPSS or Microsoft Excel and then use the software to calculate the F statistic. You will want to look at the F statistic and p-value on the output from SPSS. We can see that the main effect for frequency has an F value of 1.4 and a p-value of 0.136. The main effect for intensity has an F value of 10 and a p-value of 0.001. The interaction effect for frequency and intensity has an F value of 5 and a p-value of 0.045. You can see that there is a symbol for the p-value for main effect for intensity and interaction, which indicates significance at an alpha level of 0.05. So since the p-value for the interaction for frequency and intensity is less than 0.05, you can reject the null and conclude that groups differ based on frequency and intensity together. Here's the graphical representation of VO2 max after a 1-month training period based on 2 exercise intensities of 65% and 85% of heart rate max and 2 exercise frequencies of 3 and 5 days per week. The main effects is where there is significance in a specific factor only, regardless of other factors. How we interpret the main effects for frequency is that it indicates that both 3 and 5 days a week don't provide different VO2 max values when pulling across the different intensity levels. However, individuals who trained at a higher intensity, such as the 85% level of intensity, significantly outperform the individuals who trained at 65% of the intensity. This is looking at the main effects of intensity. The interaction suggests that training at 85% of maximum heart rate for 3 days per week results in the highest levels of VO2 max. Occasionally, a significant interaction will occur without any significant main effects. Also, a general rule of thumb is to first look at the interaction, and if there isn't significant, you would then look at the main effects. A two-way ANOVA is the most basic form of a factorial ANOVA. A factorial ANOVA allows for a simultaneous evaluation of 2 or more levels of independent variables. Factorial designs are referred by the number of levels of each of the independent variables. So a two-way ANOVA can be referred to as a 2x2 ANOVA. You can also add an additional level, which would make it a 2x3 ANOVA. One of the independent variables would have 2 levels, and the other independent variable would have 3 levels. So going back to our previous example, frequency would still have 3 and 5 days per week, but intensity you can add 75%. So you would have 65%, 75%, and 85% of different intensity levels. Factorial analysis can also be extended to more than 2 independent variables. So for instance, if you added running distance with two different levels, such as 1 mile and 1.5 miles, you would then have a 2 by 2 by 3 ANOVA. It should be noted as the more independent variables you add, the more challenging it is to interpret the analysis, especially if there are many significant interaction effects. ANOVA tests that contain at least 3 groups will indicate that there are differences among the groups. However, it doesn't indicate which groups differ. You don't know if group 1 differs from group 2 and not group 3, or if group 1 differs from both groups 2 and 3. So this is where post hoc testing comes into play. Post hoc tests are tests that follow up ANOVA to show where significant differences between specific groups exist. They are really comparing each group to every other group. You may be wondering why you should choose to perform an ANOVA with post hoc tests rather than performing a set of t-tests from the start. The biggest problem is that t-tests are designed to compare only 2 groups. Therefore, if you perform an additional analysis, this compounds type 1 error, which is concluding that differences exist, when in fact there are no differences between groups. By using a post hoc test, this retains the alpha level while providing the comparisons of each individual group to every other one. This provides a much better way to determine where the significant differences appear between groups. But there are several different post hoc tests to choose from. Some examples are Fisher's least significant differences, or LSD, Tukey's honestly significant difference, HSD, Duncan's multiple range, and Newman-Kuhl's. Each post hoc test differs in the amount of adjustment to alpha. This means that some post hoc tests are more conservative and less likely to lead to rejecting the null hypothesis, whereas others are more liberal and more likely to lead to rejecting the null hypothesis. The last thing we'll talk about and the final type of ANOVA we'll discuss is the analysis of covariance, or ANCOVA. ANCOVA is used to adjust for a variable that covaries with the independent variable and may impact the outcome of the test. This is usually performed where group means are known to be different at the beginning of an experiment. A variable termed covariate has an impact on the values of a dependent measure and can impact the results of the analysis. ANCOVA statistically controls for covariate that may have an impact on the statistical outcome. Some examples are age, initial blood pressure, and BMI. In addition, ANCOVA allows for statistical control when other methods of control are not possible. Another way in which ANCOVA can be used is to adjust for initial group differences. There may be at times in which random sampling may be impossible and group differences in pre-test scores need to be accounted for. So in a sense, you are making a fair comparison at the start of an intervention. Some things that need to be completed by Monday, November 30th by 11:59 p.m. is completing quiz 10 and also submitting your t-test and ANOVA assignment. The last thing is that your literature review is due Friday, November 20th by 11:59 p.m.